at University of Colorado Boulder. The way Galois got to know him is through a DARPA Muse program. He was the Colorado PI on the program, is currently working on DARPA Stack, and as a whole is interested in helping developers build better software. So, Evan, thank you for visiting us, and go for your tech talk.
Una, thank you very much for. Oh, I should turn this on. Una, thank you very much for the introduction. I'm really excited to be here. Thank you very much for inviting me. From the outside, I've always seen Galois as like, oh, so awesome, like the things that you do in terms of bridging university and the industrial world. So I'm really excited to be here. I guess as this is set up as a meet and greet, I thought I'd just give a very high-level overview of some of the things that we've done as part of the DARPA Muse program, just really the highlights, so that hopefully we can have further discussion from that. All right. So here's the team at Colorado that have been working on the program. And we've been working on one of the most important problems of our time. That is that, unfortunately, Angry Birds has stopped. That is, of course, we've seen a crash in our application, in our Android application. And of course, in today's modern and connected world, any crash gets magnified by the crowd. That is, let's say we have our, in order to release our application, we immediately have to be subject to the whims of the internet and reviews and such. And so we have things like our app crashes and freezes, and maybe because it crashes and freezes, people think it's spyware. So as the poor developer trying to fix this so that the reviews can go up, there's really just a cry for help. I don't know what caused the crash. Right. Now, what's often new at every application update is bug fixes and optimizations. So maybe that's an opportunity. And of course, that is the premise of the Muse program. So that is, we imagine tomorrow's world of programming as a social world where, of course, as an Android developer, or if you're an Android developer, you're not by yourself, but you expect that there's a community out there of Android developers that you're communicating with. So that is our hope always when we're faced with this situation of this cry for help, is that someone else, maybe because their boss made them, poured over dumps and log files and whatever you name it for hours and hours, came across the same issue, committed a bug fix into some repo that I can just somehow lift and transfer over. That's the dream, right? And of course, that's the premise of the Fixr project, is can we at least partially realize this dream of transferring bug fixes with program analysis and synthesis. So, okay. So, and further on, to kind of explain what are maybe causes in Android applications, here's one example of an actual pull request that we found. So there's some sort of crash, right, that it can't execute the task. The task is already running. Of course, like again, as the developer, why, what happened? I have no idea what caused the crash. I haven't really found out how to reproduce this, but let me make some guess. But there's some issue, like the bug comes from violating some implicit framework protocol rule.
I'm slightly behind on because while I'm distracting, that's really distracting.
Ah, okay.
Sorry about that.
Yeah, no problem. I'll wait. It wasn't distracting me because it was behind me, right? All right. Okay. Thanks, Rob. So I haven't really found how to reproduce this, but the bug came from some violating, I don't know what, but some implicit framework protocol rule that I didn't really know about, right? And then I do something, I search the internet, this is the process, right? I go to Stack Overflow and I hope to figure out something, and then I do something, and then I have this question mark of, well, I did something, is this fix really a fix? In fact, we actually looked at this particular pull request and said, like, okay, it's kind of a workaround to probably make it happen less often, but it really isn't exactly I think we would say is the right fix or whatever. Okay. Okay, so big challenges, of course, is first challenge is that if we think about just the corpus that we took a snapshot some years ago, right? The corpus has 16,000 repos, 500,000 commits, almost 3 million change Java files in there, just looking at a Java corpus, right? 1.4 million commit relations. So it's really the scale, and so the scale of things that the artifacts in the corpus, but also the scale of the Android framework. If we're looking specifically at Android applications, well, Android is a really complex framework, has hundreds of API packages, thousands, and this is, of course, as of a couple of years ago, some time ago, when we took these numbers. I'm sure it's only much, much bigger. Right. So the Fixr project must find relevant patterns from a large, messy corpus in the context of a large, messy framework. Yes.
What is it in your mind that makes something a bug versus a feature? So can I use this framework, say, oh, you implemented this feature, I want to port it to my app. Is that a different use case or the same?
Probably a slightly different use case. If you will, our focus would be saying that there are lots of, in terms of what I mean by a protocol rule, is like how I, as an Android app developer, need to interact with the framework, how to program against the framework. That's something that should be common across all applications. And in fact, that'll be our main hypothesis that allows us to actually do something.
Okay, this is a known, and that's what distinguishes is you know what your kind of final objective is.
Yeah, I guess it's, yeah, the objective is to make sure I'm following the Android rules, if you will. Okay. But, excellent question. So the second challenge is, well, understanding this very complex behavior. An application, we think of it as just a tiny app, but really is actually a very complex piece of software. To understand that very complicated event-driven behavior. So anyone programmed an Android app or at least played with a tutorial at some point? Okay, great. Great. So the first thing that you need to do is implement a bunch of callbacks to handle different events. And then the first thing you do when you start developing an Android application is you open the documentation and you see a picture that looks something like this, called the Android Activity Lifecycle, and he's like, okay, this is the rules I need to follow. But really, for those who probably have played with this, have said like, okay, this is kind of like there's some hidden truth behind here, or there's some much more nuances than what you read in the documentation, and that's probably at least the root cause of your pain at the start. Right? That is that these callback ordering constraints are not a static thing, but really a much more dynamic thing. If we think about the actions that the interactions that you have between the Android framework and you as an application, you sort of have to think about all the possible actions that can go back and forth between you and the framework. Right, so a big challenge here for the Fixr project is that we must have ways to reason about these complex protocols between the app and the framework that correctly handle these events. Okay, so, all right. So together, this kind of splits our project into two pieces, one that focuses on the mining side to mine frequent usage patterns. Right? That's, if you will, the focus here is looking at the app code independent of the framework to try to identify patterns. So we mine the relevant usage patterns. The patterns are snippets of app code divorced from the framework. And then the other half then is to understand the behavior of these app edits within this particular framework, a very complex, big Android framework. So we have to understand how the patterns behave in this event-driven framework to determine if we have a particular fix or something like this. So we have been, for the last few years, developing techniques on both sides for mining relevant patterns and understanding the behavior of those patterns. Okay. All right. So, so the perspective from the app developer, I guess, that we envision in kind of the suite of tools that we've developed, is that you have your application that you're working on. You're going to go out into the world and have some tools to be able to search for relevant patterns and be able to inspect those patterns from the corpus to better understand the bugginess in your application and potentially find some fixes or alternatives. Then from there, you might need to better understand the behavior of your application. So you need to somehow be able to script or test your application to generate relevant user interactions so that you can understand how your app can behave in different ways with respect to what you looked at earlier. Then in order to maybe understand the documentation or to further this triage process, you need to be able to synthesize explanations about why particular interactions trigger crashes. So really understanding what is that protocol rule in the framework. So we have some ways to try to learn what's happening inside the framework. And then from that, you want to ultimately be able to like make some change, some patch to your application and verify a change in fixing that defect. Right? That is, we want to enable tools that allow you to interactively search, test, understand, and verify to ultimately be able to transfer a bug fix. All right, so of course that generates the kind of suite of tools that we've developed as part of the program. So Big Room is a tool, a mining tool for, maybe I'll switch over here because I can't read the slide here, or the glare. It's not helping. Maybe I can stand here. Is a mining tool for finding protocol programming patterns conserved across corpora. Then we've also spent a lot of time and effort in thinking about the verification side. So the Veravita tool is a dynamic verification tool for checking that an app respects event-driven programming protocols. And in terms of that understanding what the framework does and what the protocol should be, developed a tool called DroidStar that is an active learning tool that synthesizes behavioral specifications of event-driven framework classes. And then to be able to do that sort of playing with apps and interactions, we developed this tool called ChimpCheck. It's a property-based testing tool for interactive apps, which allows us to mix automation and human insight in that testing process. So, thanks again. Okay, so again, I won't have the time to get in depth in all of these projects, of course, so just try to give the highlights, and then happy to have further discussions and questions and so forth. So please ask questions along the way, whatever you like. So first, we're going to try to mine for correct API protocol usage patterns. So that is this premise that other developers also use the API extensively and understand maybe how it goes. So the idea is that if we pull from the corpora, that we can identify somehow correct patterns from that. Of course, how we're going to do that. And the underlying hypothesis is that is a sort of popularity hypothesis that correct API usage is something that's conserved across lots of repositories. So while, of course, lots of work has been done in mining and maybe mining within a project in terms of so forth, our hypothesis is if we just take random arbitrary developers who are not really necessarily communicating with each other, if they're somehow using some things that are the same, those are probably the things that correspond to protocols in terms of using with Android. Yes.
So I imagine that correct API usage is a pretty complex condition and maybe a little fuzzy. So
Yes.
that could involve like the ordering of different API calls and then like the properties of the input data to those API calls.
Mm-hmm.
What level of depth can this protocol mining find those properties to, or like what level of specificity?
Right, absolutely. So these protocols, of course, have ordering constraints and things, and many of those things are important, and we want to capture as much as we can in terms of that. And so we end up with a representation that captures quite a bit of that kind of constraints. And I'll come back to that. So, excellent question. Okay. Okay. So, I think the question here, of course, is like, in order to be able to capture what is correct, there's a lot of sort of dependencies on that. And so I'll get back to that. Okay, so again, how do we identify correct patterns? The underlying hypothesis here is that if it's common usage across repositories, that corresponds to correct. Okay, again, because this is not something that has been stated or specified by anyone, and they're relatively high-level usage properties, so it's not something we can just sort of bake in and so forth. Okay. And then something that's maybe incorrect or anomalous is that something that's maybe, we can also use this for bug finding, right? That is, if it's uncommon across repositories, but almost like a correct pattern, that's probably also a nice indicator of a potential bug. Okay, so that's the underlying hypothesis for this particular work, right? Of course, we have to validate this popularity hypothesis, kind of sounds reasonable. But if you will, one of the main goals of this work is to provide some evidence, either for or against this hypothesis. Okay. All right. So a little bit to your question is, how do we get expressive patterns? Well, what we actually do is extract a fairly detailed representation of the program, borrowing a term from some prior work called a groom. But basically, what that is capturing control and data flow dependencies in a method. Okay. So we strip the app method to just the API calls, and then capture the control and data flow dependencies between them. Right. So the second hypothesis here is this program dependency hypothesis, that the patterns, in order to get correct API usage, need to capture both these fairly detailed things of control and data dependencies, implying we need graph-based representations. So the main contributions of the Big Groom project really are that we actually did this and got it to scale to a reasonable amount, right? Is that we extract these grooms from the repository. We cluster these grooms by a set of frequent methods and group by isomorphic grooms. And then we determine how these patterns differ and form a sort of lattice of patterns. So we compute this sort of graph embedding relation to be able to classify these patterns into popular, probably correct, or uncommon but close to a common pattern as anomalous. And of course, what we see as that preview here is that there is some evidence that this popularity implies correctness if we have representations that are this deep. Now, of course, the technical aspect is that we do this pattern mining and classification to validate this popular hypothesis, and it requires fairly deep computation to do this kind of graph isomorphisms and graph embedding computation. And the challenge is, of course, being able to limit that kind of deep comparisons to scale. Okay, so this was published at Sainer 18. And so if we had this capability to compare graphs and compute graph isomorphisms at scale, then we have this possibility to be able to do code search based upon these lattice of patterns, to be able to highlight similarities and differences, and then potentially be able to do bug detection and repair and that sort of thing, that if you have this anomalous pattern, you're very close to a popular pattern, but you're missing something, and then the thing that you're missing is maybe to add this close call. Okay. Questions? Yes?
So how much kind of specific knowledge, how much work did it take to set up these patterns and to set up the notions? You presumably have a metric on them that's kind of also very domain specific. How hard was that? And then how?
Yep.
Yeah, just give me some idea of
Sure.
the work on domain specific knowledge.
Yeah, so in fact, the underlying thing that we wanted to do here was minimize any sort of domain-specific knowledge, right? This is in essence, this is a spec mining process, right? We want to get a specification of how to use, if you will, like this example, how to use this database API, right? So we don't want to build that in. We didn't go in with the database API thing, right, or knowledge. We're trying to extract that from common patterns and seeing whether that's possible. Okay, so then the issue is, what are the kind of features that are important to capture patterns? And I think this was your question. And we arrived at least capturing control and data dependencies were really important. So we can think about very simple sort of program representations like just like n grams, 2 grams, 3 grams. We actually tried that, and they weren't really sufficiently precise to capture these protocols. And we also went on the other deep end of trying to compute points to analysis on applications and using those artifacts. While that could get us better usage patterns, the scalability of that was essentially impossible. So in the end, we're actually still computing at the end, very detailed graph isomorphism computations. There's a SAT encoding to do that, so it's really relatively heavyweight stuff that's happening. So the challenge here, of course, is how to minimize that, how to do as much sort of filtering up to the point so that you can compute these relationships, these ultimately conceptually deep relationships with minimal amount of computation.
So given that these patterns are taking into account control dependencies, how sensitive is the approach to, say, standard transformations that a compiler might do to control structure, like loop unrolling or something that messes around with a conditional statement? Are you actually saved by that because you're doing isomorphism checking, or is there?
That's a very good question.
Yeah.
I think the answer, as most of the time these things, yes and no. So because we are not just looking at the AST, the sort of the graph structure does save us in many cases in terms of loops and that sort of things like this. The things that is really sensitive to is interprocedural inlining. So if you will, most of our false alarms come from like, well, if we just inline here, that'd be fine. But then how do you decide on which inlining you do? So for the experiments here that I'll present here, we just did no inlining, right, as a baseline, sort of making some assumptions that many of the protocols that matter don't need that. But of course, you can immediately imagine where it does matter. Someone has a common cleanup method or something like that they call or something, and we would miss that. So excellent question. Okay, so let me give you the highlight of this popularity hypothesis. So we want to evaluate this popularity hypothesis. So we took 542 apps from GitHub, and from that computed about 70,000 graphs or grooms. The whole process that I described generated 410 popular patterns in 194 clusters. So in those clusters, we sampled randomly 30 of those, and then did a categorization and tried to understand exactly what these patterns capture. Okay, and so then the categorization that we did is, okay, one, whether it's a just wrong pattern. Two, whether it's like capture some sort of customary thing. Three is that you really should follow this pattern, otherwise you'll get some weirdnesses. So an example might be like, oh, you'll get a button without any text on it or something if you don't follow the pattern. So it's not a crash, but you probably need to do it. And then four is something that you have to follow, otherwise you will get a crash. Okay. Okay, so actually, 30 of those clusters, and then of the things that are classified popular, we consider both the most popular and the least popular that crosses some threshold. So that gets us 60 patterns to examine. And what, I guess the top level thing is that we found no anti-patterns, that if you followed the pattern, you would get actually something wrong in your application. And most of them are actually in these two categories here. 86% are these like best practices or obligatory. So, with this stuff, we can't get 100% concrete, bulletproof evidence, but some evidence that the popularity hypothesis holds. Okay. All right. So just to kind of give a sense of the results, there's a demo on the Muse portal of this. But basically, a very rough demo here where you can, do some sort of search. That if you're the developer, you can imagine, hey, am I using the DB API correctly? And then you would see a set of method calls defining the cluster for this particular pattern, and then be able to explore the popular patterns, here ordered by popularity and by edit distance. And then you'd be able to sort of go in and find the real code snippets on GitHub that sort of contributed to creating this pattern. And then if you select one of those, you can sort of compare your code with the code of the pattern. Okay. Yes?
How did you decide which APIs to search for? Did you just dynamically learn sets of frameworks?
That's over the process. So everything. So first, you just have the list of anything that's Android.blah is an API method, and then of course how these become grouped together to search patterns is like then there's that sort of clustering process of saying what are the most commonly co-occurring methods, and then that's the basis to then go in and try to build the graph-based patterns.
You currently have live this database that has its client information. And
Right.
how did you decide on which projects to inform with the 500-something set you started?
Just what we could gather.
Manually?
Yeah, I mean, it wasn't anything. It wasn't anything deliberately set in terms of picking the applications. Just what we could gather. So.
I was curious. Did you notice what you discovered to be this pattern? Did they match with what was in the documentation?
Excellent question. I didn't include that slide, but there are definitely like places where we found inconsistencies with the documentation. Of course, ones that are consistent, but also ones that are inconsistent. So many places where you go to the Android documentation and it's just the raw sort of auto-generated blank Java doc sort of thing. So many such instances. I should have had some of those slides here.
So are you going to talk a little bit more about about the representation you used and what the metric was on it for doing clustering and stuff?
Not specifically, but I think we could, maybe talk further about that offline or something like this.
Okay.
But high level is control data dependencies in terms of the kind of strength of the representation.
I guess my question is really, was there some kind of, this is an obvious kind of metric to use and it worked well? I guess my experience with doing any kind of data stuff is that you try the obvious thing and it just fails and you get some do, some don't. And you have to do a lot of work trying to refine the metrics that you use or the algorithm you use. So I'm trying to understand where your stuff falls.
Yeah, I mean, I think you're absolutely right that there's always the sensitivity to things. In terms of, I think, where we landed, in terms of how much tweaking happened at this point of saying this representation, relatively little. Of course, there are thresholds to decide and things like this to experiment with, but they weren't. Yeah, I mean, this is a very qualitative judgment call, I suppose.
Was it sufficient to have the sources for your analysis, or did you actually need to do something about the build system?
I think this was more of a limitation of our infrastructure, is that we actually took built applications to be able to run it through soot, essentially. So we did have built applications, not necessarily a limitation of the overall approach, I guess. But yeah, limitation in our implementation. Okay. All right. And we're currently working on trying to scale this up, talking with GitHub about it, and seeing if we can deploy this as a GitHub app, at least a proof of concept of this idea. Okay. Yep.
So one kind of thing that you see in crypto APIs sometimes is that the value you generate from one API call has to be consumed by another API call. So it's sort of like a typescape property, I suppose. Something like that.
Yep.
Is that something that you guys can deal with, where you've got kind of like data flow between different API calls?
Yeah, and that is a very important property, and it shows up a lot of places. So that data dependency, I think, is extremely key. And the things that we missed in the very lighter rate representation, where we got a lot of noise because we didn't capture that previously. So this representation does capture that data flow from, it was produced from this method and then consumed by this other method. Now, it doesn't reason about what that value is, and sometimes with crypto APIs, you do need to know what that value is. That's the particular whatever. That wouldn't necessarily be captured by this. So again, it's always this sort of trade-off between how semantic you are versus how lightweight you are, how lightweight syntactic you are, I guess. Excellent question. Okay, all right. So, switching gears a little bit. So, if there are no more questions on the sort of mining aspect, I'll talk a little bit about the reasoning, and I'll watch the time. We have till noon, is that right? Okay. All right. So, So let me talk a little bit about the dynamic verification tool. Okay. So back to this, Android is, a nightmare discussion. Right. That, okay, so as I said, or as we kind of said, like, okay, you're going to start your, tutorial on building an Android application. So you need to define a bunch of callbacks to be called. So the first thing you learn when you open your tutorial on Android is you define something called an activity, which is kind of your main component, or if you will, window of your application. And so your apps are implemented by essentially defining callbacks that when, hey, your application is started, and you need to create a window, then you define the onCreate method, callback, and then the onDestroy to react to events. And as I kind of sketched, we say that there's something called Android activity lifecycle, is that these are the orders that the callbacks that you define for your activity are called, that first is created, then it's resumed, then maybe it's paused, and then resumed and paused until it's ultimately destroyed. Seems all totally reasonable. Okay, and then as I kind of alluded before, or is it right? that the control flow in the app is dictated by this lifecycle ordering of callbacks. Okay. So then you start to program your app a little bit more, and you say, oh, well, I need something to handle like a button. So I define some sort of click listener so that when it's clicked, I do something. So I define a callback for onClick. And somehow in my thinking, if I'm the app developer, I need to like update my thinking about the lifecycle. So where is it that click can happen? Oh, I guess in the sort of active state of the activity, this onClick callback can happen from the user. Okay. All right. Then because when the user clicks the button, then I need to launch some sort of background task. So, okay, so this click, I sort of augment my thinking, right, that this click can only happen when the activity is active. And then it starts that task, and then I need to do something when the task finishes. So I define another callback, this onPost execute to happen when that background task finishes. And then so how to even put that into my model of how it can happen? Well, can it happen anywhere? Well, not quite. It can only happen once. But actually it can only happen once after this execute below that's been called, right? So it just kind of becomes this kind of, well, the life cycle is all pretty and nice and so forth. Now my thinking gets a lot more clouded and muggy, right? And then it's actually worse because maybe when I execute, I actually finish this activity, and that actually there's actually more edges to the activity lifecycle if finish is called. That, if you will, is not really even in the documentation. Okay. So just thinking in terms of lifecycle gets kind of out of hand quickly. So what we really need is a re-examination of callback control flow constraints and how to validate them. Okay. So that's basically what we focused on in the Veravita project, is taking a fresh re-examination on this callback control flow problem. That is, we formalized the glare, I need to stand over here, formalized how do we think about this app framework interface in a modeling language for callback control flow, which then allowed us to derive a way to think about verifying traces along this interface. So verify the absence of alternate life state races, if you will, and I'll explain this a bit more in a bit. And then a way to validate those models, to validate a model that are of these traces independent of any app or analysis. Okay. And and this is being published upcoming in eCoop this summer. So this is a little bit of a preview. So what I mean by these races is that the capability that the Veravita tool provides is something like, hey, you have a non-crashing trace from an app with a latent bug. That is, like, one of the rules here is that execute can only be ever called once. It's like a single-use task, right? So in the kind of code that I showed is like, well, if the user can click multiple times, then execute can be called multiple times, and that would cause a crash. Okay, so this app doesn't crash because the user happens to click once, but it has that latent bug. Can we sort of rearrange or replicate the events such that we can exhibit a particular crash? Okay, that's the kind of the essence of the tool. Okay. So the tool sort of explores all possible ways in which you can reorder the events of the trace with respect to a particular life state model, the model that we develop. And then in order to be able to do this, the challenge, of course, is that model has to be precise enough to verify the cases where they're incorrect, and that can cause us into sort of weirdnesses where we don't know if this model is a sound over approximation of behavior. So then we also have an approach to be able to validate these models. And it's through this sort of re-examining of callback control flow do we get both these halves of verification and validation. Right. Okay. All right. So anyway, the overall capability is we have a more trustworthy verification because the models that we use in order to do this verification can be validated with a corpus. Okay. All right. Of course, lots more technical details of what that modeling language looks like and so forth. Of course, I'm going to skip that now and just give the highlights. So first question is, are this kind of more detailed monitoring, this re-examination of callback control flow necessary to distinguish buggy from fixed apps in real-world Android applications? That is, if we look at some sort of out in the wild fix, right? We have trace from a buggy app version that should produce an alarm. In general, that's actually very easy to do. It's very easy to build a tool with lots of false alarms in this case. Then can we take a trace from the fixed app version and be able to verify that, and be able to not alarm? Okay. That turns out to be the main challenge. So we took 6 protocol rules where an illegal state exception could be raised. Okay. Then we took 5 open source applications and then had a human user use that app for 5 minutes to generate 50 traces, interaction traces, because we want to really test very deep behavior. So that's why we went with the sort of manual tracing here in this case. So then, so then the results, right? So here are the particular framework calls that could raise an illegal state exception if you call it in the sort of wrong framework state. Here are the traces where that particular API call is used. Here are the ones that after triage later can be verified, right? And then we looked at different essentially modelings. One which is, if you will, the kind of trivial sound model where all callbacks are always possible, are always enabled. Okay. And from that, you can verify 20% of those traces. Then we look at a model where you just have those lifecycle constraints about ordering of callbacks. Okay. And that allows us to verify 24% of the traces. And it really takes that sort of full power of reasoning about the sort of back and forth between callbacks and API calls and the sort of dynamic changing of callbacks to be able to verify 85% of those traces. So our life state modeling language is needed to go from 24% to 85% proven, if you will. Yes?
These constraints, do you get those from running the app with kind of random inputs or something? Or how do you know what the constraints on the callbacks are?
Yeah. So the modeling language that we define essentially gives those constraints, but of course, how do we get the model that we specifically run against these traces? And at this point, that's developed manually by essentially trying to prove these traces correct. Okay. So, yeah. Okay. Of course, the next step is to mine those, but we'll get to that a little bit. Okay. Right. So I think actually a more interesting thing is, of course, we know, of course, that we need precise modeling and so forth. And in fact, the state of the practice is that we write those specifications and we try to do our best job, and then we run it with our static analysis tool or whatever. And then we say, okay, I did my best in terms of getting a model that's sound, and I, whatever. And I hope for the best. So here we said that we actually took the perspective that this is just really complicated in terms of whether we know we're kind of getting more precision at the cost of soundness. It's just really, really hard to know in terms of this callback control flow. So we evaluated kind of the soundness of taking that kind of life cycle and augmenting it, so forth, that kind of standard practice, and see how much trouble we get if we were to use that. Okay. So that is, we want to ask the question, is model validation necessary to avoid modeling mistakes? So on the previous slide with our modeling approach, all of those are verified and the models have been validated across the whole trace corpus that we have. That is, we also have 2,400 or so traces generated automatically from various different applications. So we take everything we got plus the manually generated traces, and we fully validate the life state models that we used on the previous slide against those traces. And now what we want to do is validate a more standard model. So one that just writes down the activity and fragment life cycles of Android, so those basic main components, and when those sort of UI listeners are registered and attached to active activities. So it's sort of kind of the state of practice if you're doing Android analysis. Okay. And we actually derive those directly by reading the FlowDroid source, which is a well-known static analysis tool for Android. And then we conservatively, to be fair, right, any other callbacks that might happen, just we say, okay, that's fine, that's enabled, and that doesn't count against them. And then the question is, well, how sound, if we just took that approach of adapting life cycles, how sound is that process, right? And so roughly, there's more detailed categories here, but I guess I should break it down. So the first category is really just they intended to model this kind of callback control flow, but it was incorrect. There's some aspects that are incorrect but not modeled, and then the nice purple part is where there is no unsoundness, where it is sort of captured by the model. Okay, so then there's two ways to look at this data. One is amongst all of our traces, how many steps do we get to before we realize some unsoundness of the callback control flow model? And also here in terms of, so that's this x-axis. And then the number of traces that get that far. And then this one is for traces of different lengths. How often are they classified as having some unsoundnesses? So of course, kind of as expected, if they're very short length traces, then there's a fair amount of them where no unsoundness is detected. Okay.
So just to be clear, these are comparing the observed traces against the model extracted from FlowDroid that they have, the sort of like the static model of
Correct.
what the life cycle should be.
Correct. Correct. Exactly. And that's, of course, just Java code and a particular revision that we have to sort of extract.
Right, yeah, and that's another question. Do you have like a sort of timestamps on the applications from which the traces come? Because is there any concern that the life cycle has changed over time and it's kind of hard to figure out what Google is thinking there?
That is very true, and I think that's a very important point you bring out in terms of a threat to validity. I mean, we froze for our experiments a particular version, Android 6, which is already a little bit dated. So that would be some sort of issue if you're trying to look across the history in different Android versions. I think in terms of this modeling, it's really at the kind of top level, more stable stuff, because everything else we kind of just say, it's okay, and it doesn't count against them.
They add things all the time, and it seems like that shouldn't be a problem for what you described.
That's right. That's right. Okay, but anyway, the bottom line punchline here, whoops, in terms of this is that about 1/3 of traces have bad modeling, right? So half have bad or unmodeled things in the first 24 steps. So this first box is 24 steps, and about half have some bad. And of course, it gets harder to be sound as you get further along in more steps. Okay. All right. Questions? Okay. So anyway, just to kind of get an idea of what's the data there, right, is that, again, a little web demo on the Muse portal that allows you to see, like as the developer, hey, I want to see how the API call is affected by callback control flow. I can sort of sketch the callback control flow trace I expect by editing an example or entering one or something like this. And then I can verify that trace against some particular sensitive API call properties or something. Right? And then I can see if it's unverifiable or whatnot against applying our tool and seeing if it's unverifiable, get a counterexample, the usual bit. Okay. All right. 15 minutes. All right. Any questions on that? Okay. I promise you the other two tools I'm not going to go in much depth, so 15 minutes is okay. All right. Okay, so I enjoy this interactive, so I won't necessarily save extra time because we'll have this interactive dialogue. Okay. Okay, so then the question is, so in the previous thing, everything is like the models are handwritten, and of course that's automated by graduate student hours, if you will. It's very expensive. Sorry, joke. Right, so we of course want to try various different approaches to do mining or whatever. So one aspect that we've done, of course, is that, well, the Android framework, we want to get those models. The Android framework is not that small, but this big, right? Again, thousands of API classes, tens of thousands of API methods, blah, blah, right? So then one thing that we've done is at least learn a limited set of callback control flow models where we have a single object interface. So this works well at the leaves of kind of very simple objects that are kind of self-contained. Like, for example, countdown timer. You can cancel the countdown, and then at some point it finishes, and then you can register, or you can get a register callback for finish, tick, or you can start it, of course, right? So relatively self-contained things. So, but still, with some sort of API documentation like this, you have questions like, is it possible to receive on finish after calling start and then cancel, right? Can we call start again after cancel? You know, it's not there in the documentation in terms of, you know, what goes on here. So then this technique uses kind of an adaptation of L-star learning to synthesize probes on the actual framework, generating lots of different sequences to then learn an automata model of this API. Right, and so it says, you know, the output would say, oh, it shouldn't be possible to receive an on finish after calling start and then cancel. Or we can't start again after the run of the timer. That would cause a crash or something. Okay. So the notable results here is that on 16 common Android framework classes, so again, these kind of leaf classes, we found 5 really unexpected behaviors, of which 2 of them I think were actually probably inconsistent with the documentation. Of course, it's always a little bit of a judgment call with that in that reading, but in our sort of best estimation. So just to kind of get a sense of what that is, right, is that you would pick some sort of application class. It's generating sequences and seeing what are the sequences of calls and seeing what are the callbacks that you get back to sort of generate. So these are the API calls that are being generated by the tool. And then these are the callbacks that are being observed after you make those. And then these are the candidate, you know, callback type states, if you will, that the tool DroidStar is testing, and then eventually to converge. Right? So what do you need to give? Well, you essentially need to say what are the APIs that I care about, a particular API framework class. And then you actually specify the sort of translation from the API interface into the particular learning actions, right? The symbols of the automata that you care about. And then then the rest, then you give it to the tool to essentially synthesize those. Okay.
So just one question.
Yep.
So one of the big tricks with L-star is that the teacher sort of has to be able to validate a candidate at some point. So
yes.
Is that sort of left as a manual process, or do you?
No. So that's, if you will, the technical contributions that actually go into making it is to be able to do that with some with a reasonable amount of time, essentially. Oh. So, yeah, let's talk about that further.
Yeah, sure.
Okay. Okay. Right. So this is a good way for me to finish is with a little fun little thing, actually. I think that actually helped us quite a bit. Less sort of depth in terms of technical stuff behind it, if you will, algorithms. But I think it was actually, something that I think is really cool and actually practical and fun. Is that, okay, well, testing interactive applications is a pain, of course. The usual thing is I just can't reproduce it. So right now, if you sort of look at what we have in terms of the state of the world, you kind of have 2 choices, the kind of industry-supported thing of scripting your test, like with Android Espresso or Robotium. If you're an Android developer, you probably have used Espresso or something, where the developer describes all the user interactions to exercise the app, right? Essentially expressing click this, type this, do this, right? And then you have automated testing techniques that automatically try to learn how to exercise some app or things. And I guess examples would be thinking about SciPez or Android Ripper, where you just want to, you know, have it fuzz some way, right? However, I can't really use them together in a, you know, I can't really use them together. There's great automated stuff. There's ways I can write down what I need. And then the issue is something like, well, like my app is something like a, you know, service of some sort where the first thing you have to do is log in. And then once you log in, then you probably want to fuzz it or whatever, right? But why am I, like, if I give it to an automated tester, then it's spending all its time essentially trying to figure out a username and password, right? Which is not really where I want to test it. So I really want to be able to script that part and then let it go at it, or, you know, some combination, right? Okay. So yeah, right. Learning how to get through the login page is not what I care about. It's not the intent of the automated tools. Okay, so what we built is to enable this combination of scripted and automated. That is, you can script bits like typing the username, typing the password, click sign in, and then have at it, monkey, go do your thing, right? And so really, this is a domain-specific language for scripting UI interactions. It's a combinator library built on ScalaCheck. We really just took the ideas of quick check and property-based testing and sort of lifted it to the Android world, right? So that is now you're scripting not a single sequence like you would with generators, but as I think many people I'm guessing in this room know, like if you're scripting generators, thinking about scripting sets of tests is much more powerful than scripting single sequences. And then and then now you're able to sort of customize. You can put into your script calling into some sort of black box fuzzer if you want, or whatever you have it. So nice little bit of engineering where it was very easy to pull together ScalaCheck and Espresso, right? And the main idea is really just being able to write the generators, essentially building some syntax that then gets interpreted by our Espresso backend. Okay, so the notable result here is we were able to reproduce 4 classes of crashes from real GitHub issues. Okay, so that is demo-wise. You are able to write just Scala code in ScalaCheck, and then have ScalaCheck do the generation, and then we run it in Espresso and so forth. And then you would get the sort of execute instructions that were run through, and then if it crashed, then a stack trace on the crash, right? So you can script like adding in, you can write combinators that higher level just say, oh, every time you get here, do rotations, do various different sort of things that you might want to, do to sort of stress test your application. Okay. I think I just talked through that. So yeah, execution and generated sequence of user interactions, the stack trace. Okay, so running out of time, leave a little bit. So in summary, kind of talk through the high level of the 4 main tools that we developed as part of the Fixr project to be able to interactively search, test, understand, and verify to enable transferring a bug fix. Going from mining, searching for relevant patterns, generating relevant user interactions, learning Android models, and verifying a fixed app. Okay. So with that, I will leave you with a picture of beautiful Boulder, Colorado, to invite all of you to come visit. I hear that many of you would just move there immediately if Galois opened an office in Boulder, so you can advocate for that and then come interact with a great group of folks in the CUPLV group, which you could comment on and as coming from the group, of how awesome the group is and how highly collaborative. And I feel like a kinship in culture I've just seen from this morning, where this very open collaborative environment is really also something that I think is awesome here at Galois that we try to foster at CU. So thank you.
Thank you, Emma. So Emma's here all afternoon. We'll be here in Ever East because of lack of conference rooms. So if you want to join between like 2 and 5